So we can now look at how we can use our knowledge of acid bases to look at buffer calculations. So we're going to use the same equations that we've come across so far. So here's our acidic buffer, and we have a weak acid in equilibrium with its salt and H+. And so we can write Ka for that, and we can rearrange to find the concentration of H+, which of course we can then find the pH of. For basic buffers, if B is our weak base, then that will accept H from H2O when we dissolve it in water to produce Hb+, as it's accepted H+, and also hydroxide ions. And so we can write now Kb, Kb for a base, as so. And again, water we won't include because it's a liquid state. And we can rearrange that to give us the concentration of hydroxide ions, which of course we can work out the pH from. So let's have a look at some questions. So we've got first of all a buffer solution being made by adding sodium ethanoate to 0.5 deciliters cubed of 0.01 mole per decimeter cube ethanoic acid, and they want us to calculate the pH. So let's have a look at, first of all, calculating our concentration of H+. We can look at the moles of sodium ethanoate that we added by our mass over its molar mass. And from that, we can work out its concentration by taking that number of moles and dividing by the volume to give us our concentration. And we can then substitute our values into our expression for Ka. And if we do that, we know Ka, which was in the question. We now know the concentration. Well, they told us the concentration of ethanoic acid. We know the concentration. We've worked out the concentration of sodium of ethanoate ions, and so we can work out our concentration of H+. And from that, we can pop that into our pH equation to find our pH of being 5.46. Question number 2, slightly more difficult. We've now going to make our buffer by mixing some ethanoic acid with some sodium hydroxide solution. And so our buffer will be made in situ by our sodium hydroxide reacting with ethanoic acid to give us sodium ethanoate. So again, we're going to look at the pH, but first of all, we need to work out the concentration of sodium ethanoate we have, and also the concentration of ethanoic acid. So first of all, moles of ethanoic acid that we started with is going to be concentration times its volume in decimeters cubed. And we know we can work out the moles of sodium hydroxide that we added as well. That's the equation for sodium hydroxide reacting with ethanoic acid. And so the moles of ethanoic acid remaining, because it's a one-to-one reaction, is the moles that we started with minus the number of moles that would have reacted with sodium hydroxide. Now we can work out our concentration. Remember, the total volume is now 50 centimeters cubed because we've added 25 centimeters cubed of ethanoic acid and 25 of sodium hydroxide. And we can also work out the moles of sodium ethanoate formed, which will be the same as the number of moles of sodium hydroxide added, and work out our concentration of sodium ethanoate. So we've got those two numbers now. We can pop those into our expression to find the concentration of H+. And once we've done that, we can work out our pH, and our pH is now 4.58. Okay, we're now going to look at a basic buffer, alkaline buffer. So we've now got 0.2 moles of ammonia and 0.6 moles of ammonium chloride, and they've been added to 750 centimeters cubed. So let's have a look at how we do this. First of all, we'll work out our concentration of ammonia, and we can also work out our concentration of ammonium ions, which would be the same as our concentration of ammonium chloride. We now pop that into our expression for OH minus, find the concentration of OH minus. And once we've done that, we can find our concentration of OH minus as being 6.01 times 10 to the minus 6 moles per decimeter cubed. We can look at Kw now. Kw, of course, at under standard conditions is 1 times 10 to the minus 14. That's on your data sheet. We've worked out concentration of OH minus, so we can find the concentration of H plus, pop that into our pH expression, and we have a pH of 8.78. Finally then, we've got carbonic acid being formed when carbon dioxide dissolves in water. They've told us our healthy blood pH, and it's hydrogen carbonate to carbonic acid ratio. And it's told us the patient is now admitted to hospital, has a pH of, the patient's blood has a pH of 7.2, and we need to calculate the hydrogen carbonate to carbonic acid ratio. So again, let's just have a look. We've been told the pH of healthy blood. So we can work out our concentration of H plus ions from that. Now we know that, we can pop that into our expression for Ka. And we know the hydrogen carbonate to carbonic acid ratio as being 10.5 to 1. So we substitute those that ratio in along with our concentration of H plus, and we can find Ka for carbonic acid. Now we've got Ka, we can work out our concentration of H plus in the patient's blood, which has now got a pH of 7.2, and we can pop that into our expression for Ka, because we know H plus, we've just worked out concentration of H plus, we've worked out Ka, and we need to find the ratio of hydrogen carbonate to carbonic acid, and that gives us that ratio, which is and they wanted it the other way round. They wanted hydrogen carbonate over carbonic acid, so we swap that around, and if we do that, it gives us 6.6. So as a ratio, that's going to be 6.6 to 1. So hopefully you found those useful. That last question was actually a previous exam question, which just shows it's really just kind of like working your way through a couple of equations, and once you know those, it's just a matter of substituting the values in to find whichever one they want to take you on to the next step.